Okay, good. Right, so we got a new chapter today. We are starting a new chapter. The title is Center of Mass and Linear Momentum. So we're going to define some new things. Center of mass, probably heard it before, and momentum also, maybe, or maybe not. Okay, let's see. So let's see what they mean. Now, there is a picture here. Somebody is throwing a bat, okay, some stick or something. And as it is thrown, you can see it is spinning, right? But it's spinning around a point which is in red dot here. So that red dot is not. No, it's a parabolic motion. I mean, like when you throw something in the air, projectile motion. So it's not a circular motion. It is parabola. I mean, yeah. So, but my point here is, look at the red dot. That is not spinning. Everything is, there is an axis of rotation, is that center of rot. Everything else is rotating. So suppose you are an ant there at the center dot, you are not spinning, but everything around you is spinning around you. Okay, so that is the center of mass point. The center of mass point, the center of mass point is, you can think of it as the whole mass is concentrated at that point. So you can just kind of reduce the whole thing to that point, and we can look at the motion of that particular point, which is called the center of mass point. So whatever you apply the Newton's second law, you can apply to the center of mass point as if it is the only guy. You can just ignore the rest of the thing, and it is making a linear motion. Of course, the other points are spinning around that, but that particular point is not doing any spinning. It is only doing a linear motion. Okay. So this is why the center of mass concept is important. Also, we have another concept that is important we are going to introduce, which is called the linear momentum. Okay, so let's look at what they are. Okay, class, all clear? Shall we move on? Okay, right. So the contents is a short chapter. You know, if you go a little faster, we can finish the whole thing in one lecture, but I'm not going to do that. We will have 2 lectures and review in the, maybe I'll finish most of it, and we will continue reviewing in the next class. So it got 4 topics or sections. We will first define what is center of mass mathematically. Then we will define momentum, linear momentum, as opposed to, so it's called angular momentum, but we will only look at linear momentum now. And another thing called impulse. Then we will bring back this Newton's third law applied to internal forces. We will, now we move to not just one object, we will look at collection of objects. This we call the system. For that system, we can talk about internal forces, and internal force, and it connects to Newton's third law. Okay, that when we come there, we will discuss in details. And finally, conservation. Okay, this is why the concept momentum is important, because this momentum is something that is conserved under certain conditions. So when we have this conservation law, the law of conservation, it becomes easy for us to solve some complicated problem in terms of these conservation laws. So that is one main reason why we define this momentum. Okay, so let's begin. Let's start with center of mass. So what is center of mass definition? The mathematical formula is given here. It's like, let's say we have collection of object. Okay, it could be just a big, one continuous collection, or maybe discrete particle. So let me start with some collection of discrete particle like point-like objects, say M1, M2, and M3. We have number of different particles with their own positions. Okay, the position, like say R1, the vector position, R2 and R3. M1 is R1 position, M2 is R2 position. Then we can say the center of mass of this collection of object is given by this equation. It's simply the product of mass with the position, and sum them. So M1R1 plus M2R2 plus M3R3 and so on, divide by the total mass. This is what the definition of center of mass as a vector. But then again, we can separate them out as x coordinate, center of mass coordinate, x center of mass coordinate, and the y center of mass coordinate. And if you go to the third dimension, I'm sorry. Yeah, z center of mass. Yeah, it is similar. It is going to be, m in m1z1 plus m2z2 plus m3z3 and so on, divide by the total mass. So y center of mass will be m1y1 plus m2y2 plus m3y3, and if there are more, you collect all of them, divide by the total mass. And x center of mass similarly. Okay. Right. Don't worry, we will take particular examples and solve. Okay. So now this is very generally we giving the definition. And let's see what happens when you want to apply this to specific cases. So we have a collection of we'll start with the simplest collection of two masses, M1 and M2, that is our system. So our task is to find the center of mass of this. So here we are going to limit to the one axis only, x-axis only, because both of these are point masses. It is located in the x-axis, so there is no need to find the y center of mass. Y center of mass will be 0 because it has no distribution in the x-axis. All these, only we have 2 point masses, they are in the x-axis. So y center of mass is, you don't even have to worry. Okay, it will be the center of mass will be in the x-axis. So y equal to 0 for that. So we only need to find the x center of mass. So let's see how we do that from our definition. What's our definition? X center of mass. We have got only 2 of them. So summation of the product mx, mi, xi, divided by summation of masses. That means m1 x1 plus m2 x2 divided by m1 plus m2. So it's just a matter of substitution. So we need the x position of m1, which is x1, from the the origin of the x-axis. So 0 is here. So then we have m2, the mass, and the x2 is position. It's also given to us. Substitute, then divide by the total mass. You will get the x center of mass. Simple, right? Okay. Any question, please? Good morning. Yes. Can I continue? Yeah. Is everything fine? All right. Clear? Let me go to the next. Okay, so this is, they are showing how it is done. In this case, we have a collection of just 2 particles. It could be just a continuous mass, in which case it's not just 1 or 2 particle, it is infinitely many. You have to take small dot, we break it into many parts, then you have to add them all. But it's going to be difficult. Then we need integration to do it for a continuous object, but it is not part of our scope. Okay, we will not do that. Now we got a link here. I will play it. Okay, I will click on that link. It's some cool tricks. So it will take about, say, 2-3 minutes. Just watch it. And some nice trick with center of mass. Well, here it says center of gravity. There is no difference between, practically no difference between center of mass and center of gravity. It is the same concept, because we can show that when the gravity G is constant, which is the case for any small distances. So center of gravity coincides with the center of mass. So let me open this link. Okay, it's opening. Let me make it full screen. Okay, maybe this is an ad. So it's a YouTube. Let's, can you skip this? Okay, so maybe I'll bring the sound. So hopefully you can hear the video as well, people online. Okay, there's no need to hear the sound. I can make my commentary. Right, so this is a Pepsi can. There are some tricks with the center of mass.
Okay, so first what you're going to want to do is try to
balance
take the Coke can,
empty can,
and try to balance it on its edge. And as you let go, you'll soon see that doesn't work because the center of gravity is over the point at where it balances and it'll fall over. So this picture shows the center of gravity
when it is empty,
of
the center of mass is up
points,
somewhere in the middle,
the red dot
very high.
Where,
so if you put some water in it, you can bring the center of mass down because more heavy at the bottom.
Combined center
so the center of mass will
can
come
plus
down.
the water in
Because center of mass is m1x1 plus m2x2 divided by. So
now
when you have a m1 in the bottom mass,
so
it will be closer to the bottom and it will become more stable. You can balance. See, he fills it not all the way, he fills it at the bottom only. So thereby you bring the center of mass down, then you can balance it.
Stand on its own and it's very stable
can,
because the center of gravity is
trick,
directly
in a
above
party or with your
edge.
friends.
And
so you do something nice with physics.
Also, the water has a big role in this because it can flow.
Okay, yeah.
And it always ends up being level inside the can. That means
now
that when you tip
there
it,
are some more tricks. Okay,
the water takes the shape of the can, and as the can spins around, the water flows and retains the same shape. You realize that you can't do the same thing with, say, if the can was
balanced.
filled
The reason
with ice.
is now the center of mass is lower. That's why one of the reasons the racing cars have a low center of mass. So it doesn't. It is stable.
So this is twist on Mr. Gibbons' balancing act, where you have the fork and spoon.
Okay, now this is another trick with
glass,
center of
and all
mass
you need
rather
for this
than
is
gravity.
2 toothpicks, 2 forks, and a pepper shaker.
Well, let's wait.
So now you want to find the center of gravity of the fork first, and just try balancing it on your finger, and you'll find out that it's about right where my finger is pointing.
So where it is balanced is where the center of mass is.
So now what you do is you take the salt shaker and the toothpick, and then you stick the toothpick inside one of the holes in the salt shaker, preferably one in the middle. It makes it easier that way. And then you take 2 forks and you wedge the heads together in order to make sure they're secure. And then you stick a toothpick in between. Okay. And now you do a balance test.
So you can see he's balancing on his fingertip,
on
just
your,
the tip
finger,
of that
like
matchstick. It is balancing.
And then what you do is you transfer
That's
the
a
whole
stable
thing
balance.
onto
To explain it, a little bit.
And then you'll see that
I won't go into the details now.
contraption balances on the toothpick.
We can discuss it later.
In a 90-degree angle.
But see, the center of mass is actually
of the 2 forks and toothpick is exactly
somewhere
where that toothpick
below
directly
those
under it. So as long as you don't shift it
low, that's why we
much,
have got a
it will
stable
stay
balance.
under there, and it's pretty stable. And,
And
twirl around a little bit.
So another trick to find the center of mass very quickly, you balance a coin on a dollar bill. If you know where the center of mass is, it is easy. So the trick is to fold it into, then you know it's a dollar bill, it's uniform, so it must be in the center.
So now the trick to do is,
so
you have to fold and crease that dollar bill so that you create this V shape to make it easier to balance the coin. And once you get it balanced like that, slowly open up the dollar bill.
I will straighten it.
And you'll realize that the coin will shift and it will keep staying there balanced on that thin little piece of paper, because center of gravity is exactly where it lies on the dollar bill, right in the middle of the coin, and it'll stay there.
Well, he's holding the dollar bill, but the coin is balanced on top. Okay, all right, so let me stop that and get back to our slides. close it so it won't play anymore. Right. So that was some cool tricks with center of gravity or center of mass. Let's go to the next slide. We have a question now. So we are going to apply the formula we learned for center of mass to calculate the center of mass. The sound is good. La Vida by Coldplay. But the tricks are interesting as well. Okay, thank you, Kazi. Yep. Oops. The song. Oh, I see. I didn't hear the song. Okay. I don't know. Okay, fine. We didn't hear the song here, but probably you heard it. Good. The mass of oxygen is 16 times as large as the mass of hydrogen. We are talking about water molecule. You know what water molecule it made of? Two hydrogen, yeah, and H2O. Bakar, you're not supposed to drink anything in the classroom, okay? Because that's violating the regulation, okay? No drinks in the class, okay? No food, no beverages. All right, anyway, so, fine. So it's there, the picture is there in the next slide. Our task is to find the center of mass of a water molecule in terms of the locations of its atoms, the oxygen and the two hydrogen. So let's go to these are the answers. Let's go to the next slide. So we don't have to bother reading it. We get the question in one shot by looking at the figure. So this is the figure. What is given in the question is the bond length. Oops. Let me use the pencil. Oxygen molecule, and there is some symmetry here around this oxygen atom. Okay, you can see there is no reason why the left hydrogen should be different length from the right hydrogen. So this is symmetry axis. So let me choose as my y-axis. Okay, and I will put the x-axis at the oxygen. So the oxygen is at the location 0, 0. Origin is at the so the coordinate of the oxygen atom is 0, 0. Is that clear, everyone? Okay, is it clear? So I choose the x-axis through the oxygen atom, y-axis also through the oxygen atom. So the coordinate of the oxygen atom is 0, 0. Then few more things are given in the question. The bond length of oxygen hydrogen is given, 95.84 picometers. Pico means 10 to the minus 12. Okay, so very atomic distances, and this is also the same. And the angle between the hydrogen, oxygen hydrogen bonds is 104.45 degrees. These are given in the question. And the question is to find where is the location of the center of mass of this water molecule. It must be in the y-axis, right? Because of symmetry. It must be, it is symmetric, right? The center of mass has to be in the y-axis. That means x center of mass is 0. We don't even have to worry about it. Okay, let me choose another color and kind of ask you, the center of mass must be in this y-axis, right? I mean, because of symmetry. And let me give you some point. A, B, C, D. Which is more likely to be the center of mass of this water molecule? A, B, C, or D? Oxygen is heavier. Hydrogen, oxygen is 16 times massive than the hydrogen. You know, hydrogen, if atomic mass unit is 1, oxygen is 16. So it must be closer to the oxygen. Must be in the y-axis. But you know, if I draw the line here, it must be closer to the oxygen than to the hydrogen. So it's more likely to be, Bakar, are you listening? So more likely to be what? A, B, C, or D? D? Huh? B? Why? B, yeah, but B, I mean, hydrogen has a mass. So the center of mass must be between this line and the oxygen. So it cannot be B because hydrogen also has a mass. It will pull down the center of mass. Yeah, they have mass, although it is smaller mass. See, if you have two masses equal, say 1 gram and 1 gram, the center of mass will be in the center. Okay, if you have two equal mass, the center of mass will be at the center. But now, I lost everything. Now I know we have two hydrogen atoms here and the oxygen here. It must be between this line and this line, the line of, it must be in the y-axis first of all to begin with, and it must be between the oxygen level and the hydrogen level, but closer to the hydrogen atom, oxygen atom, than to the hydrogen atom. So it may be somewhere here. Okay, we don't know what it is. The task is to find where the y center of mass of this water molecule. So just to do that, let me go to the next slide. We want to apply into the equation. In order to apply into the equation, we need to know the masses. So mass of the oxygen, mass of the left hydrogen, mass of the right hydrogen. So the mass, if oxygen is 16 AMU, not gram, atomic mass unit, and hydrogen is 1, both of them are hydrogen. We call one hydrogen as hydrogen left on the left side, and the other one as hydrogen R on the right-hand side. Okay, fine. So what is the equation? Y center of mass is equal to mass of oxygen into Y1 of oxygen, mass of hydrogen left, Y2 of the hydrogen left coordinate, plus mass of hydrogen right, and the y coordinate of hydrogen right, divide by the total mass, mass of oxygen plus mass of left hydrogen plus mass of right hydrogen. So that is the equation. So we need the positions, y position of y and x also, but you don't have to worry about x. It's easy. Let's focus on the y center of mass. So we need the y position of oxygen, y position of hydrogen, right, left, and the y position of hydrogen on the left. From what we have been given already, we have been given this angle and this length. So the y position will be this. Let me make it black, okay, so I can refer to them by the color. This black length will be the y position of both hydrogen left and the hydrogen right. How do I get this? We have this red line, it is given 95.84, and we can get this angle alpha. What is angle alpha? We know this is 104.45, so divide by 2, 90 minus that will be angle alpha. Okay, there's just some simple geometry there. So we have the angle alpha. Then I can say the YL, also YR, is equal to 95.0084 multiplied by sine of alpha. That is trigonometry. So you have this triangle here, and we know this is 95.84, and this angle is again alpha. Therefore, this height will be 95.84 multiplied by sine alpha. So we get the y coordinate of the hydrogen atom, which is minus 58.708 picometer. You put it there. And also the right hydrogen atom also will be the same y value. Then we substitute in this equation, and you will calculate the y center of mass to be equal to, using a calculator, you will get it to be equal to 6.52 picometers. Okay, negative sign tells you it is below the oxygen atom, obviously, right? So I took this example of a water molecule simply because it's water molecules is a life-giving molecule, right? It has connection to biology, so it's a relevance, life sciences. Okay. Right, now how can we find the center of mass or the center of gravity? Experimentally, not from the equation. Let's say we have an object, a sheet, in some arbitrary shape. It is not symmetric. If it is a symmetric object like a circle, if someone asks you it's a uniform material made of the same material like say aluminum or whatever, if someone asks you where is the center of mass, what is the answer? Center, right? Geometric center will be the center of mass, yeah, where you can balance it. But if the object has a irregular shape like this, mathematically finding is one story, but experimentally we can find it. This is the method for finding the center of mass experimentally. What we do, we take a point in the periphery and tie a string to that and hang it. So the string will hang vertically, right? So you extend this line, vertical line, take a pen and draw this extension, this vertical line, and I'm going to call it AA. So let's say I draw it in black. So that is what it is. I draw a line on the object by hanging it at the point A and extending that vertical line, draw it in the object, you got this black line. Then you remove it from A, the string, and you connect the string to this point B. So hang it at the point B. Now you take a, say, red pen and extend this vertical line. And where this red line and the black line meets, that is where the center of mass is. Okay, this is a way to to find it experimentally, not using formula. If you have an irregular object, say like this pen, you hang it in one point, okay, then hang it in another point, and then draw the vertical line. Where they intersect is where the center of mass is. So that is one way of finding experimentally the center of mass, or rather it's the center of gravity point, which is equal to the center of mass. So that is okay for inanimate object, but what about something you cannot, say, a tree? So you can guess where the center of mass is. Suppose, see, if you have isolated trees, you will see we have bottom heavy, right? The leaves are at the bottom, more mass is at the bottom. So the center of mass will be lower for isolated trees. But trees in the jungle, in a forest, they have to grow taller. There's a competition. All the trees will grow taller. So the leaves will be at the top to do photosynthesis to get the sunlight. So here, since more masses are at the top, the center of mass will be high. Okay. Right, so we have a question here, concept question. So this is showing a baseball bat. Okay, the baseball bat, someone balances with your fingers, say for example, by moving the finger, and say it is balanced somewhere here. Now we have a question on this balancing. In the next slide, once the bat is balanced, let me draw it again, and say it is balanced here. Okay, this is the left side of the bat and the right side of the bat. The portion of the bat on the right side of your finger, so is equal in mass. So the mass of the right side and mass of the left side. You have to choose which statement is correct. Do you think the mass on the left side is equal to the mass on the right side? Or is it not correct?
If it's balanced, then it should.
No, but it is balanced, but you should know it is not a like this. It is not the same thickness. It was, thin this side and thicker the other side. And you are balancing. And the mass on this side is not necessarily equal to the mass on the right side. It will be balanced where the center of mass is. It will be balanced where the center of mass is. But it doesn't mean the masses are equal. Because, what is equal? Okay, let me say this is wrong. Let me take the next statement. Can you say this length is equal? The length on the left side, D, let me say D left and the D right. Do you think the length will be equal? It will be in the center? No, again, because it's not a symmetric object, right? The object is not uniform cross-section. It is thin one side and thicker the other side. And you are balancing somewhere here. So this length, right side length is not necessarily equal to the left side length. Also, the mass is also not equal. So both A and B are wrong. So this is wrong because they're saying both are correct. So the answer is D, none of the above. So what is going to be equal is the product. M1dl, MLdl is going to be equal to MRdr because of that is the definition of the center of gravity. Okay, so we discussed the center of mass coordinate. Now, what about the velocity? Say we have a collection of objects, say two objects, M1 and M2, and say this is at position X1, Y1, and this is at position X2, Y2, and we know how to get the center of mass of these without touching in this drawing. Let's talk about two masses, M1 and M2. So we know how to get the position of the center of mass of these two objects. Now we can also talk about, say this is the center of mass point. We can also talk about the point where the velocity of this center of mass point. So while this system M1 and M2 are moving independently, so we can talk about the velocity. The center of mass point will also move. When the M1 and M2 changes its position, center of mass will be in different place. So you can talk about the motion of the center of mass. So you can define, without going into the detail, I will just tell you this velocity of the center of mass is also given by a similar equation. So you have the velocity of M1, which is V1, and we have the velocity of M2, which is V2. So the center of mass velocity will be M1 V1 plus M2 V2 divided by total mass. Like we did this for the coordinates, the center of mass coordinate will be M1 x1 plus M2 x2 divided by M1 plus M2. The center of mass velocity will be M1 V1 plus individual velocity. Product of the mass is the velocity. Sum them and divide by the total mass. Okay, right. Now this thing, the product of mass with the velocity has a name. We call it the momentum. So now I talked to you, we will introduce momentum. Now we know what is momentum. What is the definition of momentum? If an object has a mass m and a velocity v, its momentum is equal to mv. That's it, okay?
So the direct proportionality between mass and velocity.
No, momentum and velocity. Momentum p The symbol we use for momentum is P.
Actually, its inverse proportional mass velocity.
Yeah.
One goes, one has to get less.
Yeah, but it has nothing to do with that. Now here the point is, what you should focus here is the definition of momentum. If an object has a mass m, and that object has a velocity v, we are going to call this product mass into velocity for that object as its momentum. That's it. It's a definition. Okay. So if someone asks you what is momentum of an object mass m and having a velocity v, it is just a product of its mass with the velocity. That's it. Okay. Simple as that. Okay. Just keep it simple. So it is nothing mysterious. We just define it to be a momentum. You may ask, why do we do this? We have a reason, because this concept momentum is an important concept. We have what is called the law of conservation of momentum, which we will touch later. Okay, so this is why we bother to define this thing called momentum. More than the mass alone or the velocity alone, the product mass into velocity, which we call as the momentum, is an important concept. That's why we define it. Okay, what about the unit? Well, mass is kilogram and velocity is meter per second. So it will be kilogram meter per second. Okay. Now, with this definition of the velocity of the center of mass, you can see this is the total momentum, because m1v1 is the momentum of m1, m2v2 is the momentum of m2. So this is the total momentum. So for a system consisting of two masses, okay, m1 and m2 having momentum p1 and p2, this will be the total momentum. So you can see, if I take the m to this side, the total momentum is simply equal to mass of the total mass of the system multiplied by velocity of the center of mass of the system. Okay, so this equation yields the velocity of the center of mass of a system. So you just take the total momentum, divide by the total mass, that will give you the velocity of the center of mass. Okay, now we got more definition. We defined the momentum, which is the mass into velocity, and velocity, and then we can say the total momentum will be mass into the center of mass velocity. So we are writing it again. The momentum of definition of a momentum. Suppose I take the rate of change of momentum, so I'm dividing both sides by the delta t, then you get this expression. Rate of change of momentum, because mass is not going to change, the constant, will be equal to rate of change of velocity. What is rate of change of velocity? It's acceleration. The definition of acceleration is how fast the velocity is changing. Yeah. So now this is, if you remember something, mass into acceleration is what? Newton's second law, net force. That is the Newton's second law. Mass into acceleration. Yes. Now we have an alternative expression of the Newton's second law. We saw the Newton's second law. This is what we thought, right? I mean, it is what we were told. Net force is equal to mass into acceleration. Now we have another expression for Newton's second law. So we can say net force is not equal to mass. It is correct, okay, mass into acceleration. We can also say the net force is equal to rate of change of momentum. So we don't have to tell about the mass separately and the momentum separately, I mean velocity separately. We will say the net force is equal to, when you apply a net force, it will make a change, it will change the momentum. It will have a rate of change of momentum. So whenever you apply a net force, what it will do, it will change the momentum at a certain rate. So this is another expression of Newton's second law. Actually, when Newton formulated his law, this is how he gave it. He gave it as the net force is equal to rate of change of momentum. Okay. All right, people online, are you all with me? I need some feedback, please. Are you listening to me? Are you asleep? Reem, okay, thank you. Thank you, Iba. Right, let's move on. Right, did I miss something? Yeah, I missed one slide. Okay, here. Now I can rewrite, so I can bring the delta t to this side. I can say, if you apply a force on an object, and suppose it act on that object for a period of delta t, the product, the force into the duration, is equal to change in the momentum. Okay, bring the delta t to as a to this is what we had in the previous slide, right? I'm going to bring it to this side, then I can put it this way. So this tells you the product, the force into the duration through which the force is acting, is equal to change in the momentum. So when you apply a force on an object for a time period of delta t, what is the result? It will change its momentum by the same amount as this product. So we getting another law, which is called the impulse momentum theory. But anyway, we are going to make a new definition. I'm going to take this product. When a force acts on an object for a duration of delta t, this product is called the impulse. Okay, F into delta t is called the impulse. When a force acts on an object for a time period of delta t, the product force into that time period is called the impulse. And we are defining something new now. Okay, so and we give the symbol J for impulse. Okay, when you see the symbol J, you should know that it is referring to the impulse of the force which act on an object for a period of delta t, and it is equal to the force multiplied by delta t. So this is the definition of impulse. And you can see, therefore, we have this theory. The impulse is equal to change in the momentum. Greater impulse mean the momentum will change more. Small impulse mean the momentum will be changing less. But the impulse is function of two things. It is force and duration. So when the force is greater, impulse will be greater. I mean, the change in the momentum will be greater. And also it can be greater when the duration is more. So both going to play the part. And we call this product as impulse. More impulse mean more change in the momentum. So positive impulse will make the momentum increase. Negative impulse will make the momentum decrease. It's a vector. Momentum is a vector because defined as the force multiplied by delta t, it will have the same direction as the net force. Now, more on this impulse. Let's say I take an example of hitting a ball with a bat. So this bat will apply a force on the ball. So the ball will experience an impulse which is equal to the force that is applied on the ball multiplied by how long the bat is in contact with the ball. You know, when you hit something, it is not going to be in contact for a long time. It will be a fraction of a second, right? Millisecond or whatever. So the duration is small. So let me call it delta t. So the impulse on the ball will be the force you apply multiplied by delta t. But do you think this force is a constant force? Not necessarily, right? It is not constant, but we can approximate it to an average constant force. This is how we do that. If I draw this force that we apply with the ball on this bat on this ball, is actually this, it will be like this, a pulse. When it is touching the ball, it will start with the zero force and the force will dramatically increase very fast to a very high value, let's say like 1000 Newton or 10,000 Newton or whatever, very quickly. Okay, this whole thing happened in millisecond or less than a millisecond. So it will come to a very big value, then it will drop down fast. So it is not a constant force. The force you apply when you hit a ball with a bat, it will be something like this. So it is not, if someone asks you what is the impulse from this force, it is difficult to use this equation, because what are you going to substitute for F? It is not a single value, it is changing with time according to this red line. Okay, it will be starting with 0, come to a big value, then dies down. So that's what is happening. So to solve this problem, what we are going to say, I mean, if you write F into delta T, we are talking about, say, let's say I assume I can replace this varying force by just an average force. So the impulse, if I say it is equal to average force into delta T, it is equal to, say, this is the average force, right? And this is delta T, the duration. It is simply this area, right? Let me use a different color for this. So the average force, I will use the blue line. Okay, and this is equal to average force, and this is equal to delta T. So this, what we calculated with the average force multiplied by delta T is simply the area under this average force on this graph. Right? You understand that? Because this vertical height is average force and the horizontal width is the time. Yeah. So this is, the impulse will be this area. But how do you know this is the correct average force? The trick is you choose the average force such that that blue area is equal to the area under the actual force, the red area. So the actual impulse must be the area under the actual force. This is the actual force, it's a varying force. So you choose the average force such that the area coming from the average force, the blue area, is equal in magnitude to the red area, which is the real force. Okay, I hope you get the point. People online, Eileen, Kazi, is that clear? Can I move on? So actual forces can be varying, but if the force is varying, I cannot simply say J impulse is equal to F into delta T, because we have this problem. What do I substitute for F? F is not a simple one value, it is a varying value. So the trick is to use the average force. Okay, that is the bottom line. Anyone listening there? Okay, right. I think I will stop there. Okay, in the previous class I didn't go more than that. So I will stop there. What we are left with a few more slides. We can finish it in the next class. And yeah, then we will have this conservation of momentum. That's what we are aiming to. Okay, once we define the momentum, then we have this conservation of momentum. And using conservation of momentum, we can solve some complex problem like collision problem. Okay, thank you. See you next. I hope so. I will see, inshallah.